Hey everyone, welcome to the Weekly Space Hangout for Friday. I don't even know what day it is today. Is it the 28th? Yeah, 29th. Friday, April 29th, 2016. I'm Fraser Cain, publisher of Universe Today. This week, we've got all kinds of cool stories. We're going to be talking about Dawn. We're going to be talking about dragons on Mars. Makemake's got its own moon. And methane seas on Titan. And whatever Paul Sutter wants to talk about. Those are just Morgan stories. So joining us this week, we've got the aforementioned Morgan 4 Stories Rehnberg. Hey, Morgan.
Hey, Fraser.
We've got Paul gonna surprise us with his stories. Matt Sutter. Hey, Paul.
That's right. That's me. Always full of surprises.
Yeah, but I trust you, man. And we've got a special
I would not.
guest. Yeah, we've got a special guest who I'm sure is wondering what kind of unprofessional operation he stumbled his way into. We've got Michael Richmond from RIT. Michael, welcome to the Weekly Space Hangout.
Hi, everybody.
Now, do we know somebody who works at the Rochester Institute of Technology?
So I ran into one of your fellow Universe Todayans at the NEAF conference just a few weeks ago. She happens to be an alumna from RIT, and so she invited me to come here and talk to you guys.
Awesome. That's yeah. Nancy Graziano went to Nancy Graziano I think went to NEAF and had a great time and scooped up a whole bunch more guests for the show. So awesome. Okay, so why don't you just sort of give us a quick introduction of who you are and what you do?
So I'm a professor here at the Rochester Institute of Technology in Rochester, New York, which is the cloudiest spot in the contiguous 48 states during the month of February. And it turns out I'm an observational astronomer. Those two facts don't go very well together. I'm mostly interested in doing optical observations with telescopes on the ground, though occasionally I get to use space-based telescopes. I do what I can from here in Rochester with relatively small telescopes, but I also have friends with bigger telescopes who are at Kitt Peak or Mauna Kea, and some Japanese colleagues of mine are very kind and occasionally allow me to use some of their Subaru data. So in the times when I'm not teaching classes about physics or astronomy, then I like to do observations of variable stars and supernovae. My latest project is a small project involving Spitzer Space Telescope observations of one particular active galaxy.
Well, why don't you? If I could do one thing, you are still kind of there's a little bit of latency on your connection. So if you could turn that dial down one more, that would be great.
Sure. I'm turning the bandwidth down to very low.
Very low, but not so low that we can't actually see you. I think it should be fine. And then the other trick is don't move your head a lot. I know that sounds.
I will do my best.
Yeah, I know that sounds.
In my head.
Yeah, that would be great. Great. Okay, so can you give us some details about this research that you're doing with this active galaxy, and maybe give people an explainer on what they are?
Okay, so an active galactic nucleus is a galaxy which has a giant supermassive black hole of 1 million to 1 billion solar masses near its center. There are lots of active galaxies. We think that just every big galaxy has a big black hole at its center, but most of the black holes are pretty quiet. They just sit there and don't do much. They don't produce any radiation. Some galaxies, maybe 1%, maybe 5%, have gas near the center of the galaxy, and some of that gas circles around, falls into the black hole, but as it's circling around and spiraling in, it gets really hot. It gets a lot of radiation at all wavelengths, and in a few cases, there are jets that through some process we don't understand go shooting off into space. So those galaxies with these active accretion disks that give off lots of radiation are called active galactic nuclei. And exactly how they work is a big question, and if you want to hear, I'll tell you about how we're trying to sort of look inside and figure out what's happening near the black hole itself.
I would love to hear that.
Okay, so what we're doing is taking advantage of dust. Normally, dust is a bad thing because it blocks our view of the central portions of these galaxies. The way dust blocks our view is that near the center of the galaxy, near the black hole, the accretion disk emits lots of X-ray radiation, optical radiation, and so forth. If there were dust surrounding it, we could see those X-rays and those optical rays. But if there's dust in what's normally thought of as a sort of a donut-shaped region surrounding this accretion disk, further out away from the black hole, that dust can absorb the visible optical light, warms up the dust in these clouds, and then those dust particles radiate in the infrared. So we sort of see the light from the accretion disk indirectly, because it first gets absorbed, warms up the dust radiates in the infrared. What we've done is found one very interesting little galaxy where we can see some of the optical light coming from the center directly, a little bit it gets through apparently, but then we also see a lot of that infrared light that has hit the dust, warmed it up, and escaped. This particular galaxy, moreover, occasionally has little bursts of radiation. So for some reason, the central accretion disk gets a little hotter than usual, emits a burst of radiation that lasts a couple of days. What we've seen is we see first a little burst of optical radiation, and then after a delay of about a month, we see infrared go up as well. Why should there be this sort of gap or lag between when the optical gets bright and when the infrared gets bright? Well, the optical light goes off in all directions. It has to travel about 30 days to reach a big torus full of dust. We think that that distance between the central black hole and this dusty region is 20 or 30 or 40 light days. That's still small compared to a light year, but it's a lot farther than I'd want to drive or take a plane. After the optical radiation has traveled 20 or 30 or 40 days, it warms up the dust, and then the dust starts to radiate, and then some of that infrared radiation comes towards us. The optical light gets a head start. The infrared light has sort of a delay, and by measuring this time lag, we can figure out the distance between the central black hole and this postulated donut of dust clouds. It turns out that this galaxy is...
Oh, I was just going to say, so if I sort of understand the training that I've received from the PhD astrophysicists that join us on the show, right? This is, these are the quasars, these active galactic nuclei, and the angle that we see the quasar at, the supermassive black hole that's actively feeding, if it's pointed directly at us, we're looking right down the beam, that's the quasar, maybe even the blazar, right? And then if we're seeing it at a bit of an angle, we're going to get different varieties, whether it's a radio galaxy, Seyfert, thing like that. And in this case, you're seeing it. You're looking at the galaxies that you're seeing at an angle where that ring of dust is being heated up by the material that's being prepared to die in the supermassive black hole, and from that you're able to actually piece out how big this ring of dust is and what the what the processes are that's going from where the black hole itself is out to that ring of dust.
Yes, that's right. And a lot of people might ask, well, why don't you just take a picture and see how big the dust ring is? The problem is that most of these galaxies are so far away from us that even with the best telescopes, whether the Hubble Space Telescope or ALMA or an interferometer, if you take a picture of a galaxy, you can't see details around the black hole. You can see a big bright dot, whether you look in the optical or the infrared. So we can't just take a picture and measure the distance between the central black hole and the region where the dust is. So we're going to find indirect methods to determine this distance. And this sort of what's called a reverberation lag, or a gap between the optical and the infrared, is the method we've chosen.
Right. And so was that gap, you said like 30, 40 light days? I'm sort of thinking about that sort of in perspective with our own solar system, right? Like say it's, 8 hours out to Pluto, so maybe, I'm just sort of imagining, that actually seems small to me. Like, I would have not thought, or I would have thought, like, I know that a supermassive black hole can have a event horizon that is the size of the solar system, or, out beyond the orbit of Pluto, but then, whatever, 30, 40 times that radius, that still seems pretty tight to me, to have all of that, sort of that whole accretion disk and all of that dust getting generated. Is that bigger or smaller than you were expecting?
Well, that's a really good question. I agree. Only 20 or 30 light days sounds like a pretty small. It's, for example, sort of roughly equal to the distance from the sun out to the Oort cloud of distant comets or bodies out in the outermost reaches of the solar system. So it might sound like it's pretty small, but think this might change your mind. If you yourself were floating out in space without a space, if you're too close to the black hole, you feel pretty warm, pretty uncomfortable. The dust that's emitting the infrared that we're detecting has a typical temperature of only 400 to 500 degrees Kelvin, because it's at 30 light days away from the black hole, the accretion disk. The radiation that hits you has diluted itself to the point where you'd only heat up to 400 or 500 Kelvin. So you'd probably survive for a few, maybe an hour or two before you overheat if you're out that far. So it might not sound like a large distance in ordinary astronomical terms, but it is large enough to let you survive a few hours while you look down at the black hole and see what's happening.
Sorry, Michael, you are really garbling still, and I think the people in the chat are noticing this. Are you running like Dropbox or Google Drive on that computer?
I'm running nothing else, but I'll try closing every other tab on my browser. It is
cool.
an old MacBook Pro from like 3 or 4 years ago. Maybe it just
should be able to handle that, but sometimes things like Google Drive or Dropbox can really gobble up the bandwidth, and they can cause this. Because unfortunately, it's just like, I'm super excited to talk to you about this, but it's dropping so many packets that the audio is really not able to listen to, and yeah, and you're the only one that's breaking up. So I'm let's see. Did you close down all the other tabs on your machine? Did that help?
I can only I'll try. I could try singing a song.
No, I can still hear that it's cutting out. I'm sorry to do this, but
maybe we can try this again later.
Yeah, let's try again in a couple of weeks, and maybe we can sort of connect up and we can do a little bit more technical support and see if we can make a more stable connection. Because we were just getting to the good part where you talked about how we find the library at the center of the supermassive black hole, and now we had to lose that. So I'm really sorry, but I think we're not able to repair this.
Okay.
So. Sorry, man.
Well, sorry.
Okay, thanks a lot. All right, take care. Oh, that's just the worst. I feel so bad. Like, I know his local internet connection isn't my responsibility, but I take it all on, So I feel like it is.
You don't need to internalize it. It's all right.
I can't help it. I feel guilt for the whole world. Let's move on to the news. Let's talk about the dragon in the room.
Yeah, this was a pretty exciting week for SpaceX because they announced on Wednesday that they intend to launch and then land their Dragon capsule on the surface of Mars in just 2 years. Now, this is a very optimistic, ambitious plan that they've put forth, but if they can bring it to fruition, it's going to pull together a lot of pieces that they've had in motion now for, say, the last 5 or so years. I think one of the things that has set SpaceX apart from a lot of the other players in the space game, whether we're talking about government players like NASA or other private companies like Boeing, is that SpaceX is trying to wring every bit of technology and testing out of every one of their launches. And so they don't just launch a payload, crash that rocket into the ocean, and then say, good job, we can do that again. They try to bring on as many additional objectives as possible after they've completed their primary mission. And we've seen this over the last couple of years with all these attempts to land the rocket. But one of the things we haven't seen is that they've actually been using the last 10 or so Falcon 9 launches to test this idea of landing on Mars. And landing on Mars is a challenging thing because the atmosphere of Mars is so dramatically thinner than Earth's that you can't just pop out a parachute and float down like the Soyuz capsule does, for example, when it returns astronauts from the ISS, or even the Dragon capsule when it returns cargo from the ISS. They land with the help of large parachutes that kind of thump down and shake up everything on the inside. But when your atmosphere is only about 1% as thick as the Earth's, no matter how big your parachute is, it's never going to be big enough in order to successfully slow your spacecraft down before you hit the Martian surface. And there's basically two approaches you can take to solving this problem. One is the way that we launched the original Mars rovers, which is to basically encase your spacecraft in bubble wrap and let it bounce across the surface of Mars until it comes to rest. And then you design it so that it's self-righting and it pops the bubble wrap and sort of emerges from its cocoon. Now this works fine for relatively light and relatively durable payloads like the original Mars rovers, but you can imagine as a human, after 6 or 8 months in space on your way to Mars, the last thing you want to do is bounce across the Martian surface, and you never know when you're going to land. The other answer is to use rockets. And we've actually been doing this for decades now, because the original Viking landers used rockets to slow their descent and land softly. And of course, most recently we saw the Sky Crane lower the Curiosity rover from a hovering rocket platform. But these have, again, all been relatively light objects. The largest thing to ever land on Mars is Curiosity, and it weighed about 900 kilograms. By comparison, the empty Dragon capsule weighs about 6,000 kilograms. So we're talking about more than 6 times heavier than anything previously tried to land on Mars. And if you're talking about something that large, the sort of airbag approach isn't going to work. You're going to have to slow down. And so SpaceX had this in mind when they unveiled last year their new Dragon 2 capsule. And at the time, they said that they had built in rockets in order to provide soft landings for astronauts returning from the International Space Station. But they revealed this week that they also intend to use those rockets to slow down from orbital velocity and land on Mars. One of the tricky things about trying something like this, and one of the things that really gave people pause about the Sky Crane, is the atmosphere of Mars and the gravity of Mars are different than those here on Earth. And so you can never actually test your landing system before you try it out on Mars. And SpaceX has found a clever way of getting around at least some of those challenges when testing this idea of slowing down from orbital speeds with rockets. And that's because if you go up about 50 kilometers in the Earth's atmosphere, the density of Earth's atmosphere is actually the same as the density of Mars's atmosphere. And so every time that SpaceX has been returning one of these rockets with a controlled burn down to attempt a landing, they've also been firing it in this 20-kilometer range in the same way they would fire it if they were trying to land on Mars. And that's allowed them to collect very important information about the performance, the stability of their rockets in conditions that are much more like the conditions needed to land on Mars than the conditions needed to land on Earth.
So I was pretty surprised, I gotta say, when I read that announcement. If you had asked me 3 days ago, when will SpaceX put some vehicle on the surface of Mars, I would have said, the mid-2020s, 2025, maybe go closing in on 2030. There's a ton of things that they have to get right before they can start to do it. And then I heard the announcement, and then I sort of read what they were talking about. And they literally just have 2 things to figure out. Right? They have to be able to figure out how to bolt 3 Falcon rockets together, to make the Falcon Heavy. And they have to be able to, as you said, handle that problem of being able to re-enter and land safely in the Martian atmosphere. And it can be a completely empty Dragon capsule, and even having an empty Dragon capsule at a appropriate landing site is of tremendous value to future missions. So they're going to find that target on the surface of Mars, and then they're just going to send better equipped empty or Dragon capsule one after the other. And because they don't care about bringing anybody home, once again, Elon Musk, fiendish, brilliant.
So it is an ambitious plan, and I think it's probably much more reasonable to think of this as happening by 2020 rather than by 2018. Because although SpaceX has more or less delivered on every promise that they've made thus far, they haven't always done it on schedule. And something like putting together a whole new rocket, the Falcon Heavy, and making sure that it operates correctly is a complex and challenging process. And the Falcon 9 slipped its schedule several times leading up to some of its initial launches. And we all know that you can only make launches to Mars every 2 years. And so they have a pretty short window of a couple of months in 2018 that the Falcon Heavy has to be ready for in order to make this happen. Otherwise, right. I think it's much more plausible that they do it in 2020, but even that would still be a remarkable achievement.
So, I mean, is this it? Is this the beginning now? I mean, Falcon Heavy launches sometime this year. They get the Dragon capsule to maneuver in the way they need it with the Super Draco engines on it. And then they just start to send capsule after capsule to Mars, increasing the payload, learning more about it. And all this time, the future Martian colony is built up one piece of machinery at a time.
So I think the biggest remaining question is what their source of funding is going to be. Because industry insiders suggest that even this initial test is likely to cost somewhere between $300 and $500 million. Now that's the sort of thing that you can do once as a demonstration to prove that it works and then begin to win contracts to do things like land future Mars rovers on the surface. But you're not going to be able to continually land $500 million missions over and over again without having some sort of return or without having some sort of concrete funding base. And so far what we've seen is SpaceX, every step along the way, has developed a solid financial case for how they can make this a commercially viable platform. Whether we're talking about launching communication satellites into low Earth orbit, delivering cargo to the International Space Station, soon perhaps launching interplanetary missions with the Falcon Heavy. All of these have solid foundations from which to build. And they're going to need to put forward the case for what that solid foundation is when it comes to landing on Mars. Because the amount of cargo you would have to land in preparation for human descent to the Martian surface is going to be tremendous. And is that going to be funded by the U.S. government? Are they going to bring on private partners? Is this going to be a philanthropic endeavor? I think that's probably the big remaining question, not the question of whether they can do it or not, because as we've seen, they'll get it right eventually.
Now, I don't know if you've heard, but the U.S. Air Force said that they're undercutting the United Launch Alliance contracts by 40%.
Yeah, they just won their first contract to launch a GPS satellite this week, and presuming that goes as well as the vast majority of their other launches has gone, a steady contract from the U.S. military could be quite lucrative. We know that the government makes a not insubstantial number of launches for national security every year, and to win even a part of that contract on an ongoing basis would provide an excellent source of revenue to help develop these larger rockets that can then lift larger government payloads.
Yeah, and Musk has said that he's never taking SpaceX public. So, you can see the way they're going to do this is they're just going to drive all the profit into putting more hardware onto the surface of Mars and preparing Elon Musk's retirement home. This is all still part of the plan. I mean, I don't know. It just feels more and more reasonable as he continues to implement these audacious plans. So I will, when that spacecraft is sitting there on the surface of Mars, then we'll know it's on.
Yeah, and as a scientist coming from a scientific background, this is very exciting, even if your ultimate goal isn't to put humans permanently on the surface of Mars, because just the ability to land, thousands of kilograms of material would open up a whole new era of capabilities scientifically to do things like put a permanent and full-featured weather station on the surface of Mars, and really help us understand, well, what is the day-to-day, month-to-month, year-to-year variation of weather on the surface of Mars. Right now we have a couple of stations on the rovers that provide us with basic information, but the ability to just plop a full weather station on the surface is something we don't have the capability of doing right now, and would be immensely doable if you had this sort of much larger landing capability. And I will point out that Musk has also said that the Dragon is designed to land anywhere in the solar system. And so once you can land on Mars, it's not a big leap to, say, land on the surface of Mercury or Europa, places that don't have an atmosphere at all. Because you give up a little bit of the benefit you get from slowing down in the Martian atmosphere, but you've already overcome the vast majority of that difficulty. And then you offer a capability to explore all parts of the solar system.
Yeah. Paul, what do you think? What's your opinion?
On Mars or Musk or rockets or dragons?
All of the above into one. What's your sort of sense of like, is this bringing your science fiction future earlier than you planned? Do you think this is madness? Do you think he's lying and really doesn't intend to retire on Mars, and that this is just a way to sell more Teslas?
Yeah, I don't think he's lying. He doesn't seem. I mean, he's rich and famous enough that he doesn't really need to lie. He can just believe in something and push towards it. And I do think that 2018 is a little bit ambitious when it comes to actually getting something on Mars. He may have picked that because it is a convenient launch window coming up soon. So if he misses that launch window, there are still other options for getting to Mars. They just take longer. But if you don't have humans on board, the length of time it takes to get to Mars doesn't really matter. It's just a matter of convenience. But that said, so even if 2018 slips by a couple years or 4 years, that's still really, really close. NASA is planning scientific missions that are going to be launched in the early 2020s for cosmology or for astrophysics missions. And just to think that in the same kind of time frame that we're used to in scientific development of observatories in space, that we're going to be putting stuff on Mars on a regular basis, in that same kind of time scale, in terms of decades, not in terms of centuries, that's actually a pretty crazy thought.
What do you think about Mars being a place that people could live?
I don't know. I don't think I want to live on Mars.
No,
I'm a really big fan of the color green and blue. And just red just isn't my thing. And dust, it's sand. It's irritating. It gets everywhere. So I don't know. I mean, I'm sure there's enough crazy people with 7 billion people on the planet. There's enough crazy people who would actually want to go to Mars and live there and try to have children. It's really, 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 really difficult. If you even think of the McMurdo station in Antarctica, which is probably the most inhospitable place to have a human colony, and how much support infrastructure that requires. And they can still have free breathable air, they still have water, they still have normal gravity, and there's a tremendous amount of resources poured into that just to sustain that. And then you try to do that on the other side of the solar system with no air and with no water, or no easily accessible water, it becomes much, much more difficult. And so I think the step from going from just landing stuff on Mars and putting stuff there and carving your name in the dirt or something to actually having a fully sustainable colony is much larger problem than people really think about. It's not an impossible problem, but that is like a very, very long-term thing. So Elon Musk may get his dream to retire on Mars, and he might die 6 months later. But that doesn't mean that there'll be generations and generations of humans living on Mars.
Morgan, do you think that we have any responsibility as scientists and as human beings to prevent the destruction of the Martian habitat with our filthy bacteria? I mean, it would be really tough to perfectly clean a 6,000 kilogram vehicle and the 10 others that you drop after that, right? Like, is this, if this process begins, is the idea of keeping Mars as a sterile place just over?
Well, I think we do have the responsibility to try to our utmost to ensure that we're not contaminating other worlds with our bacteria. And there are standards in place called planetary protection that define what requirements you must sterilize various parts of your spacecraft to for going to various different environments. And we talked a while ago about how this is stopping the Curiosity rover from driving up and checking out some water that is actually less than a kilometer away from it. And that's because Curiosity was never intended to go to a place that has liquid water, and thus wasn't sterilized to that sort of level.
I say we kill it before it kills us. This is a harsh galaxy, and you don't want to wait. You don't want to make yourself a target.
Right.
We need to spread our DNA as far as we can. Yes.
It's us or the Martians, and right now they're nothing but maybe slime mold, but they might
give them a chance.
It would be an intensely human activity to meet a new yet undiscovered species of life and to make our first goal to exterminate it. And
or to eat it.
Made that mistake many times on Earth, and I'd like to think we'd at least try to not make that same mistake on another planet.
Yeah. Yeah,
but maybe it feels delicious.
Like maybe once it'll be a delicacy, but they'll never be able to bring it back because no one's coming back from Mars. So they'll just have to eat it on Mars and go, this stuff is so good. It's poplars. Okay, well, let's move on. Let's talk about a supernova, Paul.
Yeah, so there's this isotope of iron that's relatively unstable. It's called iron-60, and it has a half-life of like 2 to 3 million years. And there's always this sprinkling of iron-60, like in the solar system and in the Earth's crust. But some researchers dug up some ocean cores and really dug deep, and they found that there were 2 spikes of iron-60 in the Earth's crust. One spike happened about 8 million years ago, and then another spike spanned a region of 1.5 million years about 3 to 2 million years ago. And the only way to make iron-60 in those kind of amounts are through supernova. So the powerful explosion when a star dies has enough energy that you get all sorts of isotopes of all sorts of radioactive elements, including iron-60. And to make a spike like that on Earth means that there had to be nearby supernova that went off and kind of spread iron-60 throughout this region of our galactic neighborhood, and then it kind of rained onto Earth. And what's interesting about these numbers about 8 million years ago and then around 2.5-ish million years ago is that these correspond to somewhat interesting epochs in the history of life. They correspond to not mass extinctions, but mass die-offs, and then also they correspond to global temperature cooling that are currently relatively unexplained. So maybe there's some sort of cosmic connection there. We're not exactly sure. The supernova went off a long time ago. They're all dead now. We're in no danger right now of any nearby supernova going off. All the nearby ones have already blown their top, so to speak. So we're good on that at least. But it's just there's this interesting connection that, or interesting speculation that nearby supernova may have affected life on Earth as early as a few million years ago.
how often, and I guess how close do you need to be for one of these things to really ruin your day?
It depends on the size of the supernova, but going off the top of my head, I think you have to be within, I want to say, 100 light year. Morgan may know a better number than me, but that's like a ballpark number for one of these supernova, where the ultraviolet and the gamma ray radiation really start to annoy you.
And so you're saying that the scientists have found a layer of that iron-60, the one that's formed in those supernova explosions, in the crust at that point 2 to 3 million years ago.
Yeah, all through the crust there's always this sprinkling of it, but then there's spikes of concentrations at these two layers.
This is sort of like the Chelyabinsk, or the Chicxulub, sorry, that line, what is it called? The KT boundary.
Yeah,
right?
yeah.
Where the one that killed all the dinosaurs.
Yeah, exactly. You dig through these layers and you find extra concentrations of stuff, and that kind of points to something unusual happening to the Earth.
Yeah. And I know that gamma ray bursts are even worse. So a gamma ray burst, you can be clear halfway across the Milky Way, and if one of those goes off and the beam happens to be directed right at your planet, then it's, again, a very bad day.
Yes, many ways to have a bad day in the universe. Thankfully, it looks like our bad days are over, at least for the past few million years.
Yeah, but clearly the universe is trying to kill us all.
We just take that for granted.
Yeah. Morgan, let's talk about a cool new moon for Makemake.
Yeah, so this was a result that was published this week from the Hubble Space Telescope. And you might recall Makemake as one of the earliest discovered Kuiper Belt objects. And it was the discovery of Makemake and a few other objects like it that led to this whole question of redefining what it meant to be a planet. Now, last year we had the New Horizons flyby of Pluto that revealed to us that even if you're not a planet by sort of official definitional sense, you can still be an incredibly complicated and remarkable world. And this result tells us that Pluto is probably not the only Kuiper Belt object that's like that, and Makemake itself seems to be pretty complicated as well. One of the things that had puzzled astronomers about Makemake for quite some time is the fact that when they studied its temperature seemed to fluctuate very wildly. And this didn't make a lot of sense for something that is so far away from the sun and seemed to be pretty uniform in color. And this discovery of a moon around Makemake helps solve this problem. Because what astronomers now think is that while the surface of Makemake is probably icy and pretty light in color, the moon, which has been informally named MK2, is extremely dark, colored sort of like charcoal. And sometimes the orbit of this moon makes it visible alongside Makemake, and sometimes it's tucked behind Makemake. And the darker you are, the warmer you can be, because you're absorbing more sunlight from the sun, even at these very far away distances. And so when Makemake was visible alongside of, or even sort of in front of, the moon was visible in front of Makemake, overall the system would appear to be warmer. And when that moon was tucked behind out of view, all you would see is the colder surface of the dwarf planet, and the system appeared to be colder. Now they found this using the exact same technique that had been pioneered to discover the moons of Pluto in the run-up to New Horizons flyby. And this works by taking a series of exposures at different orientations with Hubble, and then rotating them all so that the north pole of the dwarf planet is in the same direction in each image. And what that does is the rotation helps to average out. When you're averaging out a bunch of images with different rotations, you average out all of these other sort of pits of noise and uncertainty in your observations, and it builds up the signal of the objects that are actually there. And that's what they were able to do with Makemake and MK2 to discover this moon, which is about 160 kilometers in diameter. And that's pretty large. It's about a ninth the size of the the dwarf planet itself. So smaller, for example, than Charon, but much larger and larger in comparison to its host than the other moons of Pluto are to Pluto.
But I guess this isn't that surprising, right? You know, Pluto's got 5 moons that they could tell, and some of the other dwarf planets, Eris has its own moon. So I guess it's more that it's surprising that the moon was so dark and so it was so hard to find up until now.
Yeah, that's right. We're finding moons around all sorts of objects in the solar system, not just planets, but asteroids, Kuiper Belt objects, and they're extremely useful tools because we're going to be able to discover the period with which the moon goes around Makemake. That'll tell us the mass of Makemake, and because we know the size of the dwarf planet, when we divide that mass by the size, we get the density. And density is the number one most important thing you can learn about an object in the universe, because it tells you to a pretty good approximation what it's made of. We were able to understand that Pluto was likely an object that was made substantially of water but coated in nitrogen long before New Horizons ever arrived at Pluto, because we could examine its density and realize that it didn't perfectly align with an object that was completely nitrogen or completely water. And we'll be able to do the same thing now for Makemake.
That's really cool. We only got a couple of minutes left. I know we sort of started a little late, and Paul's got to run. So, Paul, I'm going to let you say goodbye now, and then let you go, and that way you can make your commute that you got to do, and then we'll cover one more story with Morgan. So, Paul, before you go though, where can people find out more?
They can find out more by following me on Twitter and Facebook. My name is Paul Matt Sutter on both platforms. And you can also find more at pmsutter.com. There's links to all my articles and videos and whatnots. I have my own podcast, Ask a Spaceman, where I talk about space. It's kind of a theme. And then also Real Space, where I interview interesting spacey people, which featured Fraser Cain a few months ago, and that was a really fun episode.
And do it again sometime.
I need to get you back in Columbus. That's what needs
ready.
to happen.
I'm
You're ready?
I'm ready.
All right, we'll make it happen. Make it happen. And then to help support those podcasts, I'm running a Patreon campaign, patreon.com/pmsutter. That money goes to pay to make the podcast stuff because it's not free.
I know the feeling. All right, Paul, thank you for joining us this week, for putting up with our technicalities, our internet issues, and hopefully everything will be settled down for next week.
That sounds good. Thanks a lot for having me on again.
All right. Thanks, man.
See ya.
All right, Morgan, let's get into one last story, and then I think we'll let this episode limp to a landing. So let's talk about
Titan.
Let's talk about Titan. Yeah, that's what I want to talk about.
So Titan is the only object in the solar system other than planet Earth that has liquid on its surface. And it's the only moon that has a substantial atmosphere. Its atmosphere is about 1.5 times as thick as the Earth's. But Titan is located around Saturn, which is much, much farther away from the Sun than planet Earth is. And so we don't have liquid water on the surface of Titan. Actually, water in the form of ice is as hard as rock is here on the Earth when you get out to these extremely cold temperatures in the outer solar system. Instead, we see liquid hydrocarbons. And so these are things like ethane, methane, benzene, etc., that can be liquid at much lower temperatures. And Cassini, which has been in orbit about Saturn now since 2004 and will be concluding its mission next year, has been studying Titan for more than a decade. And its conclusion sort of up to this point was that Titan was covered in this large system of seas or oceans of liquid ethane on the surface. And where all that liquid ethane came from was kind of a mystery, because the atmosphere of Titan is nearly entirely nitrogen, and the only other dominant component is methane. So that would be like in our Earth's atmosphere, also dominated by nitrogen, and we also have a component of liquid water, of water vapor. And then that water vapor can rain out onto the surface and form the lakes and rivers and oceans and what have you. So where was all this ethane coming from? And this research using Cassini has shown is that it wasn't actually ethane at all. It was, in fact, methane. And this makes a lot more sense because when you have methane, you can now have this sort of complete water cycle on Titan, just like we have a water cycle here on Earth, but it would be a methane cycle instead. And they made these observations with the radar instrument aboard Cassini, which allows them to penetrate the opaque clouds that enshroud Titan. And that radar was able to penetrate all the way down to the bottom of one of these oceans and measure it that it had a depth of about 160 meters. And at the bottom was this sort of sludge of hydrocarbons, kind of a mix of all the things you could get if you took carbon and hydrogen and put them together. And if you're one of the people who thinks that Titan might be an ideal place to find life elsewhere in the solar system, a sludge of hydrocarbons is exactly what you're looking for to bring together all of the necessary ingredients to form simple life. So they mentioned that if you were to pop a boat onto the surface of Titan, you would probably be able to look all the way down and see the bottom because liquid methane is extremely clear. And it wouldn't be tinted blue like the water is here on Earth. It would instead be the sort of orangish, reddish color that makes up the Titan atmosphere.
Oh, we've got to see this.
So there are proposals to put a boat on the surface of Titan and kind of sail it around and check out one of these oceans. And in fact, in 2005, shortly after Cassini arrived, they dropped the Huygens probe onto the surface of Titan. And they optimistically designed Huygens as a boat in case they landed in the ocean. But unfortunately, they kind of plopped down on what seemed to be a mudflat instead.
Yeah, as soon as I heard this idea of a sailboat on Titan, that was one of my most, one of the missions I'm most excited about. It would just be fantastic. And now you're telling me that it would be this weird, reddish tinted, clear seas, and you could see the all of the terrain at the bottom of the sea. It just sounds fantastic. We've got to send a spacecraft there. This is just going to be amazing. So get on that, please. Okay, well, we should probably wrap this up now, sort of reaching the end of our hour. And in fact, we're going to be doing an episode of Astronomy Cast, I think, in about another half hour from now. So, Morgan, let's let people find out where and how to find more of you.
Well, you can follow me on Twitter at Morgan Rehnberg, or you can visit my website, morganrehnberg.com.
Fantastic. Have you got any more shows coming up?
Oh, we just had one last night, unfortunately, and that'll be the last one for until the end of the summer. But I occasionally show up at other astronomy-related things around the Denver area. I was at Astronomy Day last weekend. I met a fan there, and sometimes I show up at Astronomy on Tap in Denver and other things like that. So if you're in the Colorado Front Range area, swing by to one of these, and you're likely to see me and definitely come say hi.
Wonderful. Great. And once again, you can find my website at universetoday.com. You can join my Patreon, which is patreon.com/universetoday. And I want to just make a big thank you to the 512 people who are contributing to Universe Today every month. Like, you have no idea how much that means to us that we're able to create this content. I'm able to pay people salaries poorly, and be able to kind of have more and more of this content out there that you guys enjoy. So if you get value out of what you're watching here today, as well as with the Guide to Space videos and all of the articles that we're posting on Universe Today, and you want to contribute, I really appreciate everybody jumping in there and participating. So just go to patreon.com/universetoday and you can sign up. We got fun rewards and, connect closer to the content that you enjoy. All right. Well, thanks for everybody for putting up with this episode of the Weekly Space Hangout. Apologize again for causing a tree to go down, bad Wi-Fi at RIT, and that motor that just started up. So we will see all of you next week. As I mentioned, I think we have an Astronomy Cast episode starting up in like a half an hour. So apparently my internet is back up at home, so I'm going to go there and get to my proper studio. So thanks everyone for watching. Thanks to the WSH crew, as always, for helping us get everything organized and giving us the support. And we'll see you all next week.